Hello, my name is Peter Craig. I'm a statistician working in the Mathematical Science Department in Durham University. Statistics is a subject which involves the application of mathematical ideas in many areas of science and other practical endeavors. But in the A-level, the statistics syllabus focuses rather on computation of things and less on their interpretation of what they are supposed to mean. And many of the fundamental mathematical ideas are omitted, or mathematical details are omitted. So what I'm going to do today is take you through some of the material on correlation and regression and try to put back in some of the things I think are important to know about and also some of those missing mathematical details. I'm going to do it in 3 stages. The first is to look at how we look at the relationship between 2 variables and measure it using correlation. And then I'll move on to how we use that relationship for prediction in what's called regression. And then finally, I'll fill in some of the mathematics that underlies some of the standard things that are taught in the syllabus. I'm going to begin by looking at what's called the Pearson product moment correlation coefficient, or which better name for it is just the correlation. You'll also find in the A-level syllabus reference to the Spearman correlation, which is a related idea but much less commonly used. The correlation, which is usually denoted by the letter R, goes by the following formula. And we're working here originally in the first place with data which are pairs of values x1, y1 up to xn, yn. So we're approaching it here entirely from the mathematical perspective. We have n pairs of numbers and we're going to calculate this formula. If we look at what's actually involved in this formula, there are various summaries of the data. There's the average of the x values, the sample average, and the standard deviation of the x values. And these ideas should be familiar to you from GCSE. And the same way for the y values here, we have the average of the y values and the standard deviation of the y values. And we can turn in due course to calculate using this formula. You'll find, however, that this is not the formula that's usually taught at A-level. The formula that's usually given at A-level looks like this. It says that the correlation is Sxy divided by the square root of Sxx and the square root of Syy. And to fill that out a little bit, the formula for Sxy is the sum over the observations, the sum over I, of xi minus x bar times yi minus y bar. So we see elements of this formula in the formula that I've given for the correlation here. And Sxx and Syy here are given by the same formula, but if we want Sxx, we have x's instead of the y's here, and if we want Syy, we have y's instead of the x's here. And as I say, these 2 formulae will give the same answer in any particular problem, but as far as I'm concerned, it's better to approach the idea of measuring correlation through this formula in the first place, because it tells you more about what you're trying to do. You're looking here at the plot of some data that were collected from a class of psychology students who took a statistics course in Durham some years ago. What you see is the weight of the student measured in kilograms on one axis and the height on the other. And you can see from the relationship that exists between these variables that you certainly could use knowledge of a student's height to make some kind of prediction of their weight. In that process, we shall see that the correlation coefficient has an important part to play because it measures the strength of the relationship between these 2 variables in a particular fashion. We're now looking at the same data but without the numerical axes on the plot. The relationship between the 2 variables remains the same, and it's this aspect of the data that we're attempting to capture through the correlation coefficient. The numerical axes, which have been removed, contain the information that was present in the original means and standard deviations of these variables, which will be also used as part of the calculation. You'll now see added onto the data without the units on the axes, you'll see a straight line. And the straight line is there merely to emphasize the fact that the relationship between these 2 variables appears to be of that form, rather than to have some kind of curvature in how they are connected. And the reason I put the line on is to emphasize a very important part of what we're doing when we compute the correlation is we are only measuring the strength of a straight line relationship between 2 variables. Were there to be some other form of relationship between them, it would not be captured accurately by this kind of measure, and we should not be using it. So here we have a toy example rather than the real one because we want to limit the scale of the computations to just show what's involved. And I'm using the formula that's provided at A-level because it is good for computation. We have our set of data for the two variables here. This is the x values in this column and the y values in this column. And then the first stage of the process is to compute the means of those columns. So if you just look and you can do the arithmetic in your heads, I should think, you'll find that the average of the x values is -3 and the average of the y values is 2. And then the next stage in just doing it by hand is to subtract the average from each of the variables, subtract the -3 from each of the x values, and subtract the 2 from each of the y values, and you get these values here. So now for our formula for the correlation coefficient, we need three things from these. We need to know the sum of the products of these, which is what's present in this column here. So just multiplying each pair of numbers and putting them into this column and then adding them up to give 25 here. And then for SXX, we need the sum of the squares of these numbers. So we just square each number, add them up, and get 36. Square each number here, add them up, and get 24. And we compute the correlation then by taking the 25 and dividing it by the square root of each of these two numbers. It's 0.85. So this formula really is very good for the purposes of computation. But what it doesn't tell us is why I'm allowed to say that this quantity I'm computing doesn't in fact depend on the axes, on the scales on the axes in the original data, which is one of the important things we want to try and understand. Now we turn to the properties of the correlation coefficient R. It has some very simple properties. The first is that the value that you compute must always lie between -1 and +1. If you compute a value that doesn't, you have made a mistake. The second kind of property we can talk about is how we would interpret it. What does it mean to us? The magnitude the absolute value tells us the strength of the association. Whereas the sign, whether it's plus or whether it's minus, tells us whether y increases or decreases as x increases. These are facts that you're meant to know when you're doing A-level examinations. What you're not supposed to know is why these properties are particularly true, where they come from. And that's one of the things I'm going to try and talk about as we get further on in this process. There are two very important special cases, which I'll just sketch for you here. So here's a case where all the points lie perfectly on a straight line. And in that case, the association is as strong as it can be. There cannot be a stronger association between these things, and it's an increasing one, so the correlation in this case is equal to 1. The other very important special case is where it's the other way around. There's still a straight line relationship, but it's a decreasing one. So again, the line goes perfectly through all the points, but in this case, the line is decreasing, and so the correlation still has a magnitude of 1, but is negative. Cases in between, we cannot just show a list of all possible cases, but the best thing is to look at a few examples, and that's what I'm going to show you next. In the graphic you're looking at, you'll see that there are now plots for 4 hypothetical sets of data. The one on the top left, there is a strong positive association, but it's not quite perfectly a straight line. And for this example, as is indicated, the correlation is 0.99. So it's very close to 1 and positive. The top right, the points are less closely clustered about the straight line, and so the correlation is smaller in this case at 0.7, but it's still positive. The bottom left, you see a situation where where y is actually decreasing as x is increasing, but the degree of clustering around the line has become even less clear, and so in this case the correlation is -0.5. And finally in the bottom right you have a situation where there is no parent relationship at all, and in that case the correlation is 0. And it's only by looking at examples of this kind that you can learn for yourself how to interpret what somebody is telling you when they give you a correlation as a number, which is common in many scientific publications. I'd like to make one final comment about the interpretation of the correlation coefficient, and that's to look at what happens in the context where you don't get a straight line relationship, but you have a curved one. So imagine that you had a plot that looks like this, where there's a very clearly and well-defined relationship between the variables. In fact, if you were thinking about modeling it, you could probably fit some form of mathematical function through those points that would fit them almost perfectly. What do you think the correlation will be in a situation like this? Well, the answer is that you've got to think about the straight line that goes through these points and not about the fact that they all lie on some hypothetical curve here. If we draw a straight line through, we're going to have to do something like this. And it's on the basis of that that the correlation will be computed. And so the correlation here will not be 1, even though there's a very strong perfect relationship between the two variables, but the correlation here will be something around about 0.9, precisely depending on how far the points are typically from the line in this case.